Hi friend, welcome all to my educational channel Math A to Z. In previous class, we discussed about the set symmetric group S3 and alternating group A3. Okay. That is, here we take a set A with only 3 symbols 1, 2, 3. Now in this class we discuss the symmetric group Sn instead of S3 and A3 instead of An instead of A3. So here we take the set A with n symbol 1, 2, 3, 4 to n. Right? Now clearly we say that the set of all bijective mappings from A to itself are the all permutation on the set A, and the number of all permutation of the set A on the set A is n factorial. Okay, and factorial n by 2 are odd and other factorial n by 2 are even. Now we know that since any two bijective mapping, if we take any two bijective mapping, these are also the permutation from this set, then the composition of two bijective mapping is also a bijective mapping, and these two bijective mapping, that is the permutation, are like F maps A to A, also G maps A to A. So if we compose this is also from A to A, because first domain A, codomain A. Here this codomain is same, so domain A and codomain A. That is the set. This is a bijective mapping from A to A. So this composition must belongs, F composition G must belongs Sn, since all the permutation is in Sn. Sn contains all the permutation of A, that is all the bijective mapping from A to itself. Okay, so from this property we say that the Sn is closed, right? Sn is closed. So the first property of the group, that is closure, hold. We know that the composition of mapping, that is the multiplication of permutation, is always associative. So associative property is hold in Sn, right? So the second property is also hold, associative. Now, if we consider the identity bijective mapping or the identity permutation as 1, 2, 3 to n, 1, 2, 3 to n. Okay, and we name this as rho 0. And this bijective mapping as f of n or f of x equal to x for all x belongs to capital A. Clearly, if we take f, or this is named as I, clearly if we multiply or compose I with any other mapping, then we get f I composition f is f, or f composition I is also f. So I is the identity element, and this is the identity permutation also. So identity element of this set is exist. So the third property, identity. Now we know that for any permutation like f equal to 1, 2 to n, and this row is f of 1, f of 2, f of n. Okay, here f of 1, f of 2, f of n is also belongs to A, because the bijective mapping from A to A, and the f inverse is f of 1, f of 2 to f of n, 1, 2 to n. This is the inverse of this permutation, and this permutation is also belongs to Sn. So the inverse of every permutation or inverse of every element of Sn must exist. So the last property of the group, that is inverse is also hold. So we say that S3 is a group under multiplication of permutation or composition of mapping. Now we know that the multiplication of permutation or composition of mapping is not in general commutative. So we say that Sn dot is a non-commutative group. With respect to multiplication of permutation, right? And the order of this group is order of Sn is equal to n factorial. We know it. Now, if we consider all the even permutation, then this set is denoted by an. This is the set of all even permutation. Of A. Okay, and we already know that the number of even permutation is half of factorial n, because half of permutation are even and half are odd. Also, identity permutation is always an even permutation, because it can be written as 1 to 2 1 or 5 6 6 5. That is always written as the multiplication of two transposition. So it is an even permutation. Okay, so we first see that I be the identity of an. So this is the fourth property, identity element exists. Also we know that the multiplication of two even permutation must be an even permutation, because if f and g are two even permutation, then this contains even number of transposition, also this contains even number of transposition. So total f composition g contains even number of transposition. So f composition g is also even. That is, f composition g also belongs to an. So this is the first property, that is the closure. close the hold. And since An is the subset of Sn, this is the mother set, and in the mother set associative law hold, and associative property is hereditary property. So in An must be associative property hold. So second property is also hold associative. And we know that the inverse of every permutation is exist in Sn. So it is also existing in, and the inverse of any even permutation is also even permutation. So this is also a group. But here also the product of two even permutation in general not commutative. Okay, so it is also a non-commutative group, and the order of this group is factorial n by 2, and it is known as alternating group. Alternating group of degree n, but order factorial n by 2, and this is also the symmetric group of degree n, but order factorial n. Okay, so this is the symmetric group Sn, and this is the alternative group An. Okay, so this is the today's class. Thank you for watching. Thank you very much.